What's up, all you badass mathematicians? So today we're gonna take a look at the second derivative test. So we're gonna start off looking at this function x squared over e to the x, and our goal today is we're trying to find all local extrema of f of x. So the first thing we're gonna be looking for, we're gonna want to find all critical points of f. So now a critical point is going to be our candidates for our local extrema. They're places where a local maximum or a local minimum could occur but aren't necessarily going to occur. So these will be places where f prime of x does not exist. So for example, a function you can think about is the absolute value of x. So here, f prime of 0 does not exist, therefore it's a critical point, because our derivative does not exist at 0, because we have a corner. So the other place where critical points can occur when we're looking for local extrema is when f prime of x is equal to 0. So this would be if we wanted to look at f of x equals x squared, then looking at this local minimum, we know that the slope here is going to be flat. The slope of the tangent line at 0 is going to be flat, therefore the slope is 0. So the first thing we should ask is there a place where our derivative does not exist? So looking at our function, it seems that our derivative should exist for x squared, because x squared is differentiable across this entire domain. And then when we look at e to the x, well, will e to the x ever give us a 0 in the denominator? The answer to that should be no, because e to the x, if you think in terms of limits, the limit as x approaches infinity for e to the x is going to be infinity, and the limit as x approaches negative infinity for e to the x is going to be equal to, well, if we raise e to a really, really large negative number, then we're going to get back a really, really small number. So in the limit, it's going to be 0. And we also know that e to the x is going to be an increasing function. So therefore, we expect it to never have to cross the x-axis. So our denominator will never equal 0. So it seems that our function is going to be differentiable at all places. So we will not be getting any critical points from this. So next we want to figure out where f prime of x is equal to 0. So first let's calculate f prime of x. So here we can do the quotient rule, but to avoid that, I'm actually going to rewrite this. So let's rewrite f of x first. So f of x is equal to x squared times e to the negative x. So this way we can use the product rule instead of the quotient rule. So f prime of x is going to be equal to the derivative of the first term times the original second term plus the original first term times the derivative of the second term, which is negative e to the negative x. Important to remember chain rule. So now that we have our first derivative, we can actually simplify this further and factor out an e to the negative x multiplied by 2x minus x squared. So we can set this equal to 0. And let's further simplify this to e to the minus x times x times 2 minus x. So now we have a product of three different terms. So if any one of these terms is equal to 0, then the whole entire term will equal 0. So can e to the minus x ever equal 0? The answer to that should be no. And we can figure that out as an exercise to the viewer. We can figure out, I'll leave it to you to figure out why e to the minus x will never equal 0. Will x equal 0? Yes, when x equals 0. And when does 2 minus x equal 0? When x is equal to 2. So we end up finding these two critical points, x equals 0 and x equals 2. So now our second step here is classify our critical points. So our typical way of classifying has been through the first derivative test, where we can draw a number line with our critical points, and by plugging in values before 0 and after 0 and values after 2, we can deduce whether or not 0 is going to be a local min, a max, or neither, and same thing with 2. So now what we're going to be looking at is the second derivative test. So let's start out by taking the second derivative. Actually, and let's first motivate why we're taking the second derivative. So right now, at x equals 0 and x equals 2, we know that our slope of our tangent line is going to be equal to 0. So what if we had information telling us that our function at 0 was concave up? So for instance here, for f of x equals x squared, we know that we have a critical point at 0, and we also know that our function is concave up at 0. So this means that there has to be a local minimum at x equals 0. So this is why we're actually going to be wanting to take our second derivative. So if I can figure out whether or not our function is concave up or concave down at x equals 0, I can figure out whether or not we have a minimum or a maximum. However, I cannot conclude anything if the second derivative is equal to 0. Then we'd have to go back to the first derivative test. So let's take f double prime of x. So f prime of x, let's look at this line right here. So we can just do the product rule 2. Actually, let's do the product rule on this step right here. Okay, so e to the minus x times the derivative, 2 minus 2x, and then the derivative minus e to the minus x times the original, 2x minus x squared. So this is now our second derivative. So let's calculate f double prime of 0. So this is going to be equal to e to the 0, which is just 1, times 2 minus 0 minus 1 times 0. So f double prime is equal to 2. So this means our function is going to be concave up. And our slope at 0, we already confirmed in the last step that it's equal to 0. This means Therefore, local min at 0, comma, f of 0. And f of 0 here is just going to be 0. So we've classified one of our points successfully using the second derivative test. So now we're going to figure out what is f double prime of 2. So e to the minus 2 times 2 minus 4 minus e to the minus 2 times 4 minus 4. So then this is going to be going to 0. So f double prime of 2 is equal to 1 over e squared times minus 2. And this is less than 0. Therefore, we're going to be concave down. And in our last step, we already know our slope is equal to 0. So this means we have a local max at 2, comma, f of 2, which is 2 squared, 4 over e squared. 4 over e squared. Awesome. So it's still perfectly valid to use the first derivative test here and plug in for values in these intervals to try and deduce. So here, if we had done the first derivative test, then we would have figured out that we're negative. Our first derivative is negative when it's less than 0, positive between 0 and 2, and negative when it's greater than 2. Meaning our original function is decreasing and then starts increasing at 0. Right? So if we think about f, then f is decreasing here, which means it's increasing here and decreasing here. So ultimately, our first derivative test and second derivative test need to agree. And so this is also another way of saying that we're going to be concave up. So the key insight here being that taking the first derivative will give us our critical points when we set equal to 0. And by figuring out the concavity, we have all the information we need to figure out if we have a local max or local min. The only thing we have to look out for is if f double prime gives you 0, then you don't have enough information to conclude anything, which means you'd have to then rely on the first derivative test. Awesome. Thanks for watching, and if there's any feedback or questions, feel free to leave them in the comment.